Hello class, this is Gilberto Fonseca, your TA. Today we'll be talking about melting point and how to find it in mixtures of two compounds. So what is the melting point of a solid? So the melting point of a solid compound is defined by a temperature at which the solid and the liquid phase coexist in equilibrium. This is crucial to think about when thinking about melting point and colligative properties of substances, because you, if you think about freezing point as well, they actually describe the same temperature, but they describe different processes, right? So melting describes going from a solid to a liquid, while freezing describes going from a liquid to a solid. And that's because melting point is the temperature at which the solid and the liquid form have the same vapor pressure, meaning that on that surface of each state, like in ice and water, the pressure of the substances towards air it's exactly the same. So the ice can turn into a liquid, and the liquid can turn into ice. If we're talking about water, which might be strange to think about, but water, the the freezing point, we all know that the freezing point of water is 0 degrees Celsius. However, the melting point of ice is also 0 degrees Celsius, right? So don't get confused, however. Do not think of the melting point and the freezing point as the same thing, because they're not. They do describe the same temperature, however. That's the important part, because again, the vapor pressures are the same of each component of that soup. If we're thinking about water and ice, you can think of it as a soup with ice and water. But the ice can turn into water, especially if you keep adding heat, right? So vapor pressure is the pressure exerted by a substance against the pressure of air. Both solid and liquid have vapor pressure. Each component, each phase has a vapor pressure. And as temperature increases, the intermolecular attractive forces are overcome by increased kinetic energy, leading to disordered liquid. So melting point occurs, that melting as a physical process occurs because each of the atoms, each of the molecules keep vibrating, keep oscillating, and thus they come apart, right? And the more energy you add, the more hot it becomes. You go from solid to liquid to a gas finally. Sometimes you can go from a solid to a gas, um, but that's rare, especially in the organic lab. Melting point also exhibits depression, just like other colligative properties. So the melting point of a pure substance is usually expressed as the temperature range over which the solid starts to melt and then is completely converted to liquid. So rather than a melting point, a melting range is actually measured. So this is important because sometimes a specific temperature um, can't be noted. Uh, and it's actually more useful to note that range. And so a lot of times the range is wider for compounds that are more impure. However, pure compounds show sharp melting points. Sometimes it can be reported as a specific temperature. So like the range can be between 0.2, 0.5, even lower than that. But it's usually 1 degree Celsius. But once you get a pure compound that is contaminated, or just mixed with other compounds, sometimes the melting point range becomes incredibly broad. For example, your book mentions the case of naphthol, which the melting point depression constant is very big. So it gets lowered, I think like 30 degrees or something like that. But it's again, it's usually like 2-3 degrees Celsius. Um, So when the impurities are added, the melting point of this new compound or this new mixture is usually lower than the pure compound, and that's why we call the melting point depression. So again, the range usually of the pure compound is quite small, right? Usually 1 degree Celsius. But once we mix that compound with other things, whichever other things, it usually gets lowered. That melting point gets lowered, and that's what we call the melting point depression. Some compounds have a different constant for it. Compounds have definitely different constants for it, and we'll see how these affect further. So how do we find that range? There's the eutectic point, which is a point in a graph of temperature of a mixture, and the composition of that mixture, the percent composition, which is an eutectic point, is that intersection of the two kinds of mixture that you can make from two components. You can have a mixture which is overly or majority is one compound, or the other mixture that is mostly the other compound. And then eventually there will be a point where temperature can't decrease any further. It doesn't have to be 50% each compound. Just know that it's the lowest temperature from the pure compound from each of the pure compounds, right? Right. Also notice that melting point is E. That's E, the eutectic point. At this percent composition of A and B, the melting point depression is maxima. At this point, this mixture is the eutectic mixture. Something to know that is very important especially if you're going into a research lab working with water, which is usually what you will do at any lab. The eutectic mixture of ice and salt, or another name for this kind of solution is ice and brine. Brine is just water and salt, right? At this mixture, which is pretty natural to make, a 77% ice and 23% salt, the eutectic point is negative 21 degrees Celsius. This is another reason why we salt the roads when it becomes snowy, right? To lower the freezing point of water, or in other words, lowering also the melting point of ice. So these are the 5 sets of samples, 3 mixtures that you would make. But also something that you want to consider when looking at melting points, especially in the lecture portion where they'll ask you to compare compound A and compound B and ask you which one has the higher melting point or the lower melting point or whatever. You want to look at the size of the compounds. You want to look at the shape, the symmetry. The symmetry is very important because of how a compound, if it's more symmetrical, it's more bound to make a crystal lattice. So the crystal lattice is easier to remain in as a solid than actually becoming disordered and going to the liquid phase. So think about, for example, why benzoic acid and 2-naphthol have roughly the same range for the melting point. Like benzoic acid has what, 6, 7 carbons, right? And naphthol has 6, 7, 8, 9, 10 carbons, while benzoic acid has a carboxyl functional group, whereas 2-naphthol has a hydroxyl group, right? So maybe this part will account for the difference to offset the size of benzoic acid to the larger size of 2-naphthol, or I don't know, might be roughly symmetrical structure here. Think about why they have the same melting points, right? Even though they're quite different crystals. This is a brownish color and this is a whitish color, right? But onto the capillary tubes that you would be using. These are very small capillary tubes. If you were doing this with liquid, not the melting point procedure, but if you were packing these not with a solid but with a liquid, you would see that the liquid would go in spontaneously up the tube. But here you have to press constantly, like tapping into the powder, and the powder starts going in slowly. But then you turn it on, you turn it over, and you knock on the surface so that it actually packs, and it packs kind of tightly. You have to make sure that it packs tightly. You wanna think about why you want that. Well, it's because you want to evenly spread out the mixture, so that when it gets heated, the heat can traverse the solid evenly, so that not only one side gets liquefied. You want the whole area of the tube that contains the solid to start becoming melted quickly and evenly, of course. So determining melting point range using the Digimelt. If you look at the book, if you read it, you would see that there's several apparatuses that they talk about. But this is the Digimelt. It's quite easy to use. It only has one port, however, and something that you might want to keep in mind if you end up doing more of these is that the more entries, the more samples you can melt at the same time, the better, because that way you eliminate the chance of additional error. Because every time you heat something, believe it or not, the path is slightly different, right? The ramp is different. Even though you might set it at 5 degrees Celsius per minute, there's some deviation, right, with any instrument. So you want to keep it the same for the samples that you're going to take. But this has one entry, and you put in the tube with a closed end first, and here there's a little opening where you can see the melting process going on. You want to think about how this melting would look. It's a softening of solid, but what does that actually mean, right? Compared to having to the solid structure without melting, and then the intermediate stage of the melting. How is that different visually from when it actually melts completely? It's this clear liquid formation. There's a meniscus formation here. This is something else that you might see is that here in this in the onset of melting, you can see is liquid forming down here. It's one of the first things that you can see. And then the recommended ramp rates. If you did titrations in general chemistry or ever in your life, which I hope you have, once you get familiarized with one specific titration, you might figure out that you can go really, really quickly. It's not recommended, of course. It can mess up your procedures, but you can go really quickly. And once you get near the equivalence point, you go really slowly, so that you verify when the coloring has begun, right? The indicator has changed color. So it's a similar idea here. So then once you get your data, which would be from these three mixtures, 10% 2-naphthol, 90% benzoic acid, you pack it in real good in the capillary tube, you insert it, and then you heat it to 5 degrees Celsius and then 1 degree Celsius. And you would see this process melting begins here as you change the composition here. You can notice that it's pretty small range here, but as you increase the composition and it reaches the atoectic point, the difference is quite larger, right? Here you can see that the contamination or the impurity of the substances with respect to each other is maximum, right? The impurity is for each other is at the maximum. Now again, it doesn't have to be 50% all the time, but with some substances, especially since these are the melting point, the range is equal, right? So again, the broadest melting point range is the eutectic point, or it'll give you the range of the melting point. So once you do that for every single one of the mixtures, and you record your data and you plot it in Excel, you could probably do it in one go in the lab during the lab session. Then you throw away, since all this we were all working with solids, then you throw it all away in the solid waste bin. Benzoic acid, 2-naphthol, and the waiting papers. Even if it's slightly contaminated, you want to throw it away, especially since we don't label those. So if you use it and somebody walks in and wants to use it but doesn't know if it was used for anything, it might mess up their own project, right? So we want to keep it clean always. And then the used capillaries, even if they're not broken, just drop it in the glass waste sharps container, and then make sure that the Digimelt apparatus is turned off. We're gonna see that with heating mantles and heating plates. You always want to turn them off, and personally I always disconnect them, just to make sure, and perhaps to also save some standby energy, I think it's what it's called. But anyway, thank you for listening in. This has been Kiber Fonseca. Thank you.